So first of all, I want to thank the organizers and Disney for having us. And I'm going to talk about deep learning. I'm Marco Aurelio Ranzato, I work at Facebook. And so let's imagine that you are a meteorologist and you go around the world, explore the world, and at every location you measure the altitude, and for the given altitude you measure also the corresponding temperature. So nearby the sea, it is very hot, and the more you climb the mountain, the temperature drops. And so at some point, somebody comes to you and tells you, I live in a place that is at this altitude. Can you make a forecast? Can you tell me what is the temperature? And so is the temperature maybe something like this or this? I don't know. Maybe it is cooler. It's like this. So this is a typical example of supervised learning where you have input-output pairs. In this case, the input is the altitude and the output is the temperature. And the task is to make a prediction. So for a new input, you need to extrapolate and figure out what is the corresponding output. Here is another example which is more relevant for the work that we do at Facebook. We have lots of faces, and these are faces from a public data set of celebrities. And so for every face, you have an annotation that tells you who this person is. So for instance, on the first column, you have a couple of images from Schwarzenegger. And at that time, you are given a new image, and you have to tell who this person is. In this case, this person is Zidane. And you have to perform this task, although you have never seen Zidane in this pose with this facial expression. And this is another example of supervised learning, because in this case, the input is the images and the output is the ID of the person. And so again, you have input-output pairs, and the task is for a new input, tell me who this person is. So let's try to formalize this problem. So you can think that the input is a variable x, and you give it to some black box that is a function that maps x into the output that you want to predict. Now, if you have a single input, you can imagine that you can hand design this function so that it gives you the desired output. But in practice, we have many, many images, billions of images. And so we want to do well in average across all these images and also generalize well to new images. And therefore, we need to come up with automatic procedures and to make this function have also degrees of freedom or parameters that automatically we will adjust. And so basically, the key idea is to define an error function that measures the discrepancy between what your machine predicts and what is the actual, the true value. And once you have this error function, the learning algorithm has to figure out an automatic procedure to make this error as low as possible over the training set in such a way that you can also generalize well. So in this particular case, in this toy example, say that we have 4 persons that we want to identify. We can represent each person with an ID, which is a vector, which has 4 entries. They are all 0 except for one entry, which is set to 1, and this identifies the specific person. So for instance, Schwarzenegger is identified by a vector that is 1, 0, 0, 0, while Zidane would be 0, 0, 0, 1, okay? And once we do this, then we can define several error functions. The simplest is just taking the sum of the square differences between the components of these 2 vectors, what you predict and the actual answer. And in this case, the error would evaluate to 2, right? Because we have 1 plus 0 plus 0 plus 1. And after having defined the error, we can define an optimization problem that minimizes the error over the training set. And we are going to adjust the parameters to make the error as low as possible. And the simplest way to do this is by computing derivatives of the error with respect to the parameters. So The function, if you want to ground it could be anything at this point. In the simplest case, it's just a linear mapping, what you see here, this W times X. In this case, X, you can imagine that we take the image and we vectorize it. So we take the first, the values of the pixels in the first column, and then the values of the pixels in the second column, and put it in a big vector, and that's the X. And the W would be a matrix that has as many rows as the classes that we want to discriminate, and as many columns as pixels in the image. And what we are going to do, regardless of the particular function, we are going to compute derivatives. And in practice, what works really well on large data sets is not to compute the gradient across all the images, all the training samples that you have, but to do it incrementally. So the algorithm is called stochastic gradient descent. And in practice, you take, for instance, one image or few images. You compute the gradient of the error with respect to the parameters for each of these images. You average the gradient. And then you update the parameters by taking a step in the opposite direction of the gradient, because you want to minimize the error. So if you had a single parameter, and this is your error function, you start at a certain point in this parameter space. You observe a training sample. You measure an error. You compute the gradient. You update the parameter. And so you move a little bit your parameter. And then you take another training sample. You do the same procedure. You update the parameters again. And as you do this, eventually you go to the minimum of the error function, which is what you want. And the reason why you don't want to do this in a what we call batch mode, so the reason why you want to do this incrementally is because large data sets are typically very redundant. So imagine that you have a data set with 10 training samples. If they are all the same, it really pays off to, so if you compute the gradient for every training sample and then you average, you get the same gradient that you could get by just considering a single example. And so it is best from a computation point of view, in terms of time to converge, if you take just one training sample, update, then take another one, update, and so on and so forth. And so far, what I said applies to, is like a general machine learning thing. And now I'm going to customize it to deep learning. So in a regular machine learning setting, typically people extract measurements from the input. If it is images, Rob gave an example, you can compute histogram of gradients. If it is audio, you can compute some sort of gradients in the frequency time domain. And after you compute those features, what you learn are the coefficients in this matrix W. And this is what you use to make your prediction. In a deep learning system, instead, we have that the system is composed by a cascade of nonlinear stages. Each of them is parameterized by some parameters. Here W1, here you have W2, here you have W3. But again, as long as all these stages are differentiable almost everywhere, you can apply the algorithm that I described earlier on, and you can compute gradients, and you can update the parameters as you go. And yeah, the reason why we like to have multiple stages is because this is potentially more efficient, and also what we observe in natural, like in images, in audio, have a compositional structure, and we want to our network to reflect that. And as we shall see, indeed, we capture this compositionality in our network as well. So that's the general framework of supervised learning. So learning when you have input-output pairs by using gradient information. And now I'm going to talk about two specific applications. The first application is automatic speech recognition. So if you have a smartphone, you probably have tried it. It means that you speak to your phone, and automatically it will recognize what you say and will transcribe it. And let's see how it works. So it's a big system, and at a very high level, it is composed by 3 parts. And I'm going to zoom in each of these parts. Yeah, the first part is feature extraction. So you have an input waveform. So on the y-axis, you have the amplitude here, and here you have time. And the feature extraction is very simple in this case. It's just two Fourier transforms on the top of each other. And this produces a time frequency representation of the signal where on the y-axis here you have the frequency, and here you have time. Each column is representing 25 milliseconds of audio signal, and each column is, its time being is overlapped by 10 milliseconds. And so, for instance, here you see this abrupt change. So the color is proportional to the power spectrum. And so here, for instance, you see that we have an abrupt change that touches all the frequencies. And so this is something like a t, sh, that takes all the, it's very abrupt and covers all the frequencies. While here you have something that perhaps is a vowel. And you can see also the formants that depend on the harmonics that you generate because of the physics of the vocal tract. And so after we got this kind of representation, no, later. So you give it to a deep network. And so the task of the deep network is to take a small chunk of spectrogram, something like 100 milliseconds, and predict phones. Phones are primitives of sounds, something like t, r. And you want to predict this primitive of sounds for the middle frame. Actually, for this frame here, the reason being that we want to work in real time. And so you don't want to wait for too many frames in the future to make a prediction. So there is a kind of trade-off, because the more you wait and you look at the future to predict a certain frame, the better the accuracy, but then your system won't work in real time. So basically, the DeepNet maps a piece of spectrogram into a distribution of phone IDs. And then at every time step, you have a score for every phone ID, okay? And so you can build a lattice, which is a graph, where each node represents a phone ID. So in this case, you have a score of 0.2 for A, a score of 0.7 for B. And then you have also edges that with scores, because you have some probability to go from one state to another state. And now your task is to find the path that has the largest score, that is most likely, from beginning to end. And once you compose these states, you get to a word. And this search is actually constrained by the fact that the word that you are going to generate has to belong to a dictionary, has to be legal, and also by the fact that as you combine these words, they have to have some grammatical meaning in some sense. So to put the pieces together, we have some feature extraction, the DeepNet that goes from a frequency time representation of the signal to the phone IDs, and then we have some machinery that goes from, that puts together these scores for phones through time and makes the transcription, okay? And now we have a lot of people speaking on the phone, and people have transcribed what they say, and so we have, again, input-output pairs, and so we can train the DeepNet, because there is a way to go from the transcription to the sequence of phone IDs, and therefore we have input-output pairs to train the deep network, okay? And this is clearly a very difficult task because there are people with weird accent like mine. There is a lot of noise when people speak on the phone. It's difficult to separate the words, so it's not trivial at all. And the network that we use is at a very high level, something like this, where the input is this little patch of spectrogram, which is vectorized, so that's my x. Then you multiply this x by a matrix whose coefficients are subject to training. And then we need to apply also nonlinearity after this, because if you have multiple layers and they are all linear, then there is no point in having multiple layers because it is just a linear transform. So we need to have nonlinearities here. And the simplest nonlinearity is simply set to 0 the negative values. And after we do this, we get an intermediate representation. And then we apply another matrix. And actually, here I'm showing just one layer, but we can have many, many layers. And eventually, at the very top, you map into an output that with as many entries as phone IDs that you want to identify. And again, you can train this by computing gradients and using the method that I described earlier on. And so in this experiment, we use several hundred hours of speech data from people speaking to their smartphone, which was transcribed. And we have 8,000 phone IDs. And the input consists of 40 frequencies, and then we take 20 frames in the past and 5 in the future. The network overall has about 40 million parameters, so quite a lot of parameters, but we have a lot of data because if you take, say 500 hours of speech, there is a lot of these little, how many tens of milliseconds do you have? It's really a lot. And this training used 1,500 cores. We trained for 2 weeks. And every day we would process 1.2 billion frames per day. All right? So it's a lot of computation. And at the end, this is the result. So here I'm showing the word error rate, so the average number of words that you get wrong in the transcription as a function of the number of layers. And as you increase the number of layers, also the number of parameters increases, obviously. And here, I trained for 2 weeks. And what happens is that if you look, it is something intuitive, I think, that a simple model like a 1-2 layer is very fast at converging. But the accuracy, once it converges, is not as good as a model that has many more layers. And so, for instance, here the 12-layer model, after 2 weeks, hasn't really converged, and so it is slightly worse than this guy. But what happened recently with these high-performance computing devices, or when we train on a distributed framework, we can train for much longer time than we did before. So say 10 years ago, 20 years ago, they would observe that adding layers wouldn't really help. But that's just because they didn't train for long enough, or they didn't have the computational power. So actually, if you train, with these, GPUs or using clusters, you see that by adding layers, you actually do well, but you need to wait for a little bit longer. And so this was deployed early this year. All major speech recognition labs around the world are using deep networks as a component in their system. And this reduced the word error rate by a significant fraction, and it made speech recognition actually usable, because before, really nobody was using it, because even you wouldn't understand what kind of errors the system does. While now, if you even look at the errors, you can understand how to poke the system and tweak it to make it better, because it got to a point where it is usable and it makes sense. The second application that I want to talk about is object recognition at the category level. So given an image, you want to tell which objects there are. For instance, you want to say that there is a tree, there is a lake, and there is a lion. So as Rob mentioned, this is very hard because there is a lot of variability if you just look at the pixels that you get, because objects can be seen from different angles, because there is, they can be, parts of the object can be hidden by something that is in front of it. There is a lot of similarity between classes too, right? I mean, people are a bit crazy here. But fortunately, we have very large data sets that are annotated. So we have data sets that have tens of millions of images, and each image has a tag that says which object, what is the main object in the image. And so the idea is to use deep learning on this task, because again, it is map the input, an image, into the output, which is the tag. Okay? And the structure of the network is now a little bit more specialized for vision. So it is, again, composed by multiple stages, these black boxes, but each black box has a particular structure. And now I'm going to walk you through these layers. So the first layer performs convolution. So this means that if this is your image and these are the pixel values, you have a kernel or filter that is trying to look for a specific pattern. And what you do an inner product between this filter and a patch in the image. So it means that you do a component-wise multiply and then you sum. And then you report that value in the output. And you do this at every image location, okay? So what does this accomplish? So if you have an image like this, and you have a kernel that with these coefficients, once you swipe it over the image, it's going to detect vertical edges, okay? So if you look for the largest values, either positive or negative, you get all the vertical structure, all right? And so in practice, we are going to have many, many of these filters. And these filters, the coefficients in these filters are subject to training, are those things that we compute the gradients and update. And these are real filters that we learn. So you find, in this case, horizontal edges, vertical, diagonal, and so on and so forth. And these are the resulting maps that you get after you apply these filters. So here you see the horizontal structure. After the filtering approach, we need to apply nonlinearity again. And the simplest is simply to set to 0 the negative values. And then there is an operation that we call local contrast normalization, where at every image location across all the filter responses, we divide each filter response by the norm of the filter responses at that location. And this makes the representation robust to changes of illumination and contrast. So it doesn't matter if the image is dim or if you have a lot of contrast. The representation that you produce after this normalization is going to be the same by construction, okay? And the last operation that we do is pooling, where we divide this map of filter responses into regions that can overlap or not. And then we output the maximum value in each region. So if this map was reporting the output of a, say, vertical edge detector, within this region, it doesn't matter if you get a large response here or here, because you take the max. So you make the response robust to the exact location of the pattern, okay? So it's a way to achieve robustness to small transformations, in this case, translation. So this applies to multiple stages. So at the next stage, you're going to take filters that look across these maps. And so if you have, say, a map that looks at vertical edges, another map that looks at horizontal edges, at the next stage, you're looking at correlations between these two, and then you can get corners, for instance. And we'll see later some of these, what actually they do. So here I'm reporting some experiments on a benchmark that is that every year is proposed in the computer vision community. And so we have a very large data set that has 20 million images, no, actually 50 million images and 20,000 categories. So it's a very large data set. And every year they make a competition where they take a subset of it. And then they give you only the training set, they hold the test set, and then they ask for people. So all the major computer vision labs in the world, train their system, send their code, and then the organizers evaluate on the hidden test set, okay? And this is very challenging. So here I'm taking a class, hammer, that is a rigid object. And you can see that there is a lot of variability in these images. And these images were crawled from the web, okay? And the result is that what you see here, here you have the error rate in recognizing, classifying these images. And here you have different methods that participated to the competition. And the first column is for the deep net. And it basically almost half the error rate. And the previous year, the error was around here. So you can see that all the standard computer vision approaches pretty much leveled out at around 26%, and the deep net did much better. And I want to point out that, and we will try to understand why it performs so well in a second. Before we go into that, I want to point out that in this case, we train on, they train on 1 million images, but we had 60 million parameters. And if you know about statistics, they tell you that in order to estimate a variable, you need maybe 10 observations. And here we have fewer observations than parameters. So overfitting is really a serious problem. And the way that they prevented overfitting was in several ways. One way was to simply transform the input images, so to do random translations, flipping left-right, in order to augment the training set. That's a simple trick. Another trick was to inject noise in the internal representation in order to make it more robust so that it doesn't really focus on silly details of the noise in the input data. Together with standard machine learning regularization methods, like penalizing the square norm of the parameters. And the other thing that I want to observe is that a forward pass, so to go from the input pixels to the class label, takes about 800 megaflops. So 800 million multiply adds are necessary in order to perform this prediction. And this is quite a lot of computation. And that's why, also in this case, it was important to work on high-performance computing devices, in particular GPUs. So here you can see some examples of test images. You have the image with underneath the ground truth label. And beneath, there is the prediction, the top 5 scoring classes predicted by the network. And when the bar is red, it means that that's the correct class. And as you can see, it may make some mistakes, like in this case, but the mistakes are kind of reasonable. And besides, now the network has been trained on lots of images and has learned generic features. And these features can be used also for other tasks. And here is a retrieval task, because you have several layers of representations, and you can take the representation at the very top layer. And now you take a test image, you compute the corresponding feature, and you compute the corresponding feature for every training image. And now what you can do, you can compute the similarity between these features. In particular, you simply sum the square of the difference between the two vectors. And then you can rank the training samples according to this distance. So here we have the images in the training set that are the closest in feature space to this test image. As you can see, for instance, if you look at this elephant image, these images are pixel-wise rather different, but semantically they are very similar. And the network clustered them together because you train in a supervised manner to do a many-to-one mapping. So now, thanks to Matt Sealer and Rob Fergus, so to the work that people did in Rob's lab, we can also try to understand, a little bit, try to get an insight about how the network works. And so far, I've been trying to convince you that we are using a black box approach, and now we are trying to make these black boxes gray and to look inside at the artificial brain. And so we basically stick, like a little bit neuroscience too, we stick a probe in the artificial brain and trying to look at what these neurons do. The way that we do this is by presenting images at the input, and for every image, we take a unit, a computational unit, say one entry in the feature vector, and we record the corresponding value for every input image. And some images will yield a very large value, some others a small one. And now we can sort the images according to the filter response that they produce. And so here you see that we have 6 different neurons, quote unquote, and the top 9 image patches that they responded the most. So for instance, this neuron is responding a lot to yellow patches. It really likes yellow. This other one to edges in this kind of orientation, and so on and so forth. But you can see that there is still some variation that is captured by this neuron. So it's not just specific to one kind of pattern. There is some variability. If you go one stage below, a layer 6, you got more interesting stuff. So you got a neuron that likes furry things, some other that likes kind of vertical structure, more regular one, something that has a white stripe in the middle, or a more complicated texture like this. If you go even deeper, you got a neuron that really likes faces, another one that likes complicated texture that I wouldn't be able to describe, another one that likes this silhouette or red stuff, pumpkins. Then we go to layer 8, we got parts of dogs, complicated texture, round shapes, man-made objects. And finally, at the top layer, as a computer scientist, I'm really happy to observe that there is a neuron that figured out keyboards. Also, you got basically more neurons that are very specific for certain objects. So like dogs, kind of flowers, kind of round yellow stuff, birds. And then another thing that we can do is to do brain damage in this artificial brain. And no animal was harmed in doing this experiment. So the network has 10 layers, and the accuracy is this, okay, with 10 layers. If we get rid of one layer, we get to 80.8%. So it is 1% worse. It's worse, but not by much. If we remove 2 layers instead, the accuracy drops by 5%, which is quite a bit. And now if we remove 4 layers, the accuracy is really much, much worse. So this shows that you really need to have a lot of layers and a lot of parameters. And this was deployed by Google in the personal photo search, also by Baidu for image retrieval. We use it at Facebook too for our products. And so in conclusion, deep learning is about learning hierarchical models where you have a cascade of nonlinear stages. In the supervised case, we train by using input-output pairs. And it works really, really well when you have very large data sets. And the main challenge is scalability. So how can you train? So if you have, say, 100 million parameters, how many training samples do you need? You need a lot of training samples. But then you need also a lot of compute power to process this data. And this has been applied to many fields, from finance to NLP and other things. And now I'll pass the microphone to Adam that will tell us how we can train these large networks without labeled data.